All right. Final part of the lecture is about viscous magmas and different eruption styles. So we'll start off talking about high viscosity lava and how it flows. So yeah, back to our kind of overview thing. We're still in the low magma ascent rate, but with the viscous lavas. So for lavas that are more viscous than basalt, so typically more than 55 weight percent silica, we get blocky lava flows. So what blocky lava flows are is they have this really uneven surface, but it's not like our lava where it's made up of these, really sharp kind of, they call them clinker, they're like these kind of shattered fragments of rock. They're these big, smooth blocks. They're angular, but they have fairly smooth surfaces. And these are described as being kind of like, you can imagine like a magmatic glacier. So they're slow-moving sheets, they're flowing at the base, but at the surface where they're cool, they're continually breaking up and pushing this rubble along. So you can see quite a steep, thick front, so steeper and thicker than an RR flow because we're getting more viscous. And actually, if we have an RR flow that cools or crystallizes enough and becomes more viscous, they can actually transition into a blocky lava flow. So in something like a basaltic andesite, we can start off with an RR flow, end up with a blocky. At the extreme end, if we have even more viscous lava, then we get lava domes. And these are typically composed of silicic but degassed lava. And the degassing part is kind of important when we talk about explosive eruptions later. But basically, under these conditions, the lava can't flow far. So it's not erupting and then flowing downhill as a flow. It's basically just growing in place like a big pimple of silicic lava. Up at the top here, we've got a massive rhyolite dome in the Andes. And down here, I put this one in because this is a picture of an andesite dome. And you can see that it's absolutely covered in rubble. So what's happening here is that as these domes grow, the edges and the sides are unstable, and so they're continually collapsing and making these kind of, they call them a talus apron. So this could be a breccia or a conglomerate, some of you might be familiar with. And so basically we can imagine that underneath this, there is some sort of fairly coherent lava dome, but the top of it's just absolutely covered in rubble. If these suddenly collapse rather than just growing and having kind of rubble tumbling off them, then it can actually trigger an explosive eruption. Now the dome covered in rubble, kind of reminds me of somewhere that we've been to in Spain. So, okay. At the extreme end, we can get obsidian flows and domes, and obsidian is a highly viscous but pretty much crystal-free lava. And when it quenches, we get obsidian. This is a felsic volcanic glass. And these flow incredibly, incredibly slowly. This is a picture of a rhyolitic lava flow from Glass Mountain in California. And this is a picture of the obsidian in it. And you can see it's pure glass. It's got, glassy breaks in it. Yeah?
What do you mean by quench?
Oh, quenched is just rapidly cooled, or cooled without being able to crystallize. So often these things show flow banding, and you can kind of see it in this obsidian here. You can see these sort of light and dark flow bands. It's probably a bit more obvious here in this. This is a rhyolite from the Aeolian Islands, and you can see that it's banded into different colors. And this flow banding is basically tracking the direction that the magma was moving in, or the lava, sorry. Go ahead.
Why do they form the bands?
The bands, I think the slight differences in composition or how much they've been able to crystallize, if they've been able to crystallize a little bit, and they just get kind of stretched out in the direction of flow. This isn't like a lava that's kind of easily mixing together. This would be like, in glass blowing where they have different colors of glass and they stretch it out and the colors stay separate, right? This is the same kind of thing. It's not well mixed because it's so viscous. So, in thin section, they look like this, and you can actually see a flow band here. And it's marked by these very subtle differences, and it's kind of these little dark patches. Maybe these are some oxides that have begun to crystallize or something. I'm not quite sure because they're way too small to see under the microscope. But basically you get this because once you get to a rhyolitic lava, it can actually be quite difficult for them to crystallize because they're so highly polymerized, they're incredibly viscous, and they're quite low temperature. So it really limits how ions can diffuse around. So it can make it quite difficult for crystals to nucleate. And once they nucleate, they can only scavenge whatever ions are in the surrounding area. It's not like, you know, our classic phenocryst growing in a magma chamber where it's floating freely in magma and you can grow a layer and then grow another layer and kind of build it up. So when these glasses quench, they can sometimes devitrify, and what this means is that in local areas they're forming these tiny little crystals. And because we have a limited ability to nucleate crystals and because we don't have much diffusion, they can grow these things called spherulites. So you can't really see them in this top image here. There's kind of like vague round outlines, but in the cross polars you can see them. And these spherulites have a really distinctive cross, a kind of an extinction cross in two directions. And what's happening here is as soon as a crystal does start to nucleate, it's basically cooled way past the point where it wanted to form that crystal. So it's what we call undercooled, and it's got all this pent up energy and it's like desperate to crystallize. So then as soon as you actually start to form a crystal, it just goes and forms this huge fan in the area, just sucking up whatever is available locally. And then it stops because it runs out of material to eat up. So these are probably quartz or a feldspar or something, and they're actually a fan of very narrow needle-like crystals arrayed round in a spherical ball, so spherulites. So these are quite distinctive features in rhyolites that have flowed rather than erupting explosively. So we kind of summarize all the lava flow styles. We can broadly treat this as a continuum where with increasing silica content, degree of polymerization and viscosity, we go from pahoihoi to AA to blocky lava flows, and then at the far end a dome. And again, hoihois can evolve into AA flows can evolve into blocky flows. Go ahead, Emma.
Where is columnar jointing placed on this?
So columnar jointing is just a cooling feature, and so it's often, as I said before, often in basalt you can see it in andesites, you can see it in some intrusions, and it's just to do with the fact that it's cooled moderately, slowly under some sort of thermal gradient, right? So in a lava flow, the top is cold, the bottom is hot, so it cools and contracts first at the top, and then the joints propagate downwards.
Can they skip a stage? So
Um,
how long
I don't think so. Yeah. Did that answer your question, Emma? Is that? Yeah. Okay. Bastian?
Why can't you have the columnar jointing in rhyolites?
That's a very good question, and I don't know. Yeah, sorry. Yeah. Leonard, you had a question? So?
Supplement to that, would a columnar joint usually be followed from a hoihoi?
So I think most commonly it's from these thick flood basalt pahoihoi flows, but yeah, as I mentioned, you can also get them from intrusions. It's not limited to that, but yeah, I have only read about them being in basalt and andesite and seen them in andesite, but I don't know. Yeah. All right, good to go. Okay, so that was it for that section. So more viscous magmas with more than 55 weight % silica can form blocky lava flows. These are all kind of magmatic glaciers with fragmented edges made of smooth angular blocks. These can be quite big, up to about 1 meter across. Even more viscous lavas, so andesites, daceites, and rhyolites can form lava domes. And as they grow, these have unstable sides that collapse to form talus slopes, talus aprons. So this could be similar to breccia or conglomerate that you might have seen in the field. High viscosity magmas can often be glassy due to limited diffusion, and they may show flow banding and devitrification textures. All good? Okay, so basaltic eruptions. So up till now, we basically have been dealing with how stuff flows, but not necessarily how it erupts out of volcanic vents and fissures. So I know this is shown in this kind of summary diagram as being like different styles of eruptions, but well, I'll get to that in a sec. On land, we have two main types of basaltic eruptions, and the first one is Hawaiian, which are very, very gentle eruptions, and these actually end up producing most major basaltic lava flows. So you might have something that's a Hawaiian eruption, and then as the lava lands, it basically forms up a hoi-hoi flow, or something like that. The other one is Strombolian eruptions. These form where you have higher viscosity and volatile contents, and these form scoria cones that we've mentioned before. And I want to introduce a concept called the Volcanic Explosivity Index, and this is basically a way of measuring the eruption intensity and how explosive it is. And they measure this using the ejecta volume. Now, ejecta are erupted pyroclastic materials, which are also referred to as tephra, that travel through the air and water before hitting the ground. So if a lava flow just came gently out of a fissure and flowed downhill, then even if it's a very, very large lava flow, the ejecta volume is very low because not much went up into the air before landing. So when we're dealing with these basaltic eruptions, we're looking at Hawaiian, Strombolian. These would be very low on the volcanic explosivity index because we're not shooting a ton of stuff up into the atmosphere. You don't necessarily have to pay attention to all of this text over here, but the big thing here is to notice that this VEI is logarithmic. So the scale jumps it jumps by an order of magnitude from 2 to 3 to 4 to 5 and so on. So when we go up one VEI, we're talking about 10 times more crap thrown into the atmosphere. So Hawaiian eruptions, they're fairly high eruption rates of low viscosity, low volatile content melt. And they make these cool like fire fountains that you can see here, or fire curtains, which is where it's more of a fissure, it's more of a linear thing. And then below those, you can see this is a Hawaiian eruption up here, where the magma is kind of shooting up in a little fire curtain, and then it's falling down into these kind of lava waterfalls and making a big hoi-hoi flow underneath. So low viscosity, low volatile content, they're fairly typical in tholiites. So Hawaiian shield stage volcanoes. If you remember, that's the main stage of Hawaiian volcanic activity where we have most of the magma being produced. You might also get them in continental flood basalts. And so they're going to be favored by high degrees of mantle melting, which will both produce a lot of lava and also low volatile contents. Strombolian eruptions happen at a lower eruption rate with higher viscosity, higher volatile content melt. So they're still relatively low viscosity, so they're behaving in a ductile manner. And what that means is that bubbles can freely move upwards through the volcanic vent. These are often happening in basaltic andesites or some andesites, and they can happen in alkaline lavas, thinking back to the scoria cones that I showed you from Hawaii. And they're favored by lower degrees of mantle melting or fluid flux melting because this is going to give us higher volatile contents that we need for this type of eruption. And basically what happens is the bubbles can move upwards through the conduit, but there might be sort of kind of a cool upper surface, and the gas bubbles might coalesce into big slugs, and these can get trapped. And they build up near the surface, it kind of domes upwards, and eventually it bursts, and this just throws out all these little ejected pieces of basalt. Now, because there's so much gas involved, and particularly this bit that's bursting, it's a region with a lot of bubbles in it that produces scoria. So that's why we get scoria cones from this type of eruption. Another kind of cool basalt eruption are lava lakes. I mean, you probably, if you end up working as a geologist, you'll probably go most of your career without ever having to deal with one of these. They're super rare, but they're really cool. So less than 10 that are continuously active. When I went to Hawaii, it was the first time in God knows how many years that Kilauea's lava lake had drained, so I didn't get to see it, which was really sad. But Kilauea had 2 until 2018, and the big eruption that happened in September 2018 actually drained both lava lakes. I think the main one, which is this Halemaumau, is back going again. But the smaller one, I think it's called Pu-O or something. That one's stopped since 2018. So these are mostly basalt, but you get some lava lakes made of alkali basalts or related highly alkaline rocks. Mount Nyiragongo in the Democratic Republic of Congo is the biggest on Earth, I think, and this is one of these very, very alkaline lava compositions. So basically what's happening is that the lava is partially filling a volcanic crater, and it basically just sits there convecting, so it forms a crust like a lava flow. But what's quite cool is if you watch videos of these, it's almost like plate tectonics going on. So you'll see sections of the crust that will actually subduct, and it will pull chunks of the crust, and you'll get new crust forming as the lava flows up into the, so it's just like, you know, mid-ocean ridges and subduction zones, but in miniature on the surface of these lava lakes. You can also form temporary lava lakes if a lava flow flows down into a big depression, fills up, you basically get a pond of lava, which will eventually solidify. Okay, so if we want to make a basalt explode, then we need some help from outside water. And these are called Phreatomagmatic eruptions. Catherine was asking before about hyaloclastites, and hyaloclastites would be the product of this type of eruption. So this is usually lava erupted in shallow water, but it can also be lava that's erupted through groundwater or beneath glaciers. What happens when the lava comes into contact with the water, it cools very, very quickly. The surface of that lava contracts and cracks, and the lava fragments into fine-grained ash. At the same time, the water is flash heated into steam, and so we're suddenly going from something that's, you know, fairly high density to really low density, massive volume expansion, and that blows everything up. So it forms a lot of, we can get features of explosive volcanism that we typically see in more silicic compositions through this phreatomagmatic style eruption. So you can get pyroclastic flows, which I'll talk about later, and big eruption columns. So these are sometimes called Surtsian volcanoes, and it's named after this basaltic volcano in Iceland that's kind of the type locality for these. And Surtsey wasn't an island, and then there was a big phreatomagmatic eruption. So basalt lava that came into contact with shallow seawater exploded, made a big eruption column a few kilometers high, and basically this island grew over just a few days. So this is the island of Surtsey in 1963, 16 days after the eruption had started, and we've already got an island forming. But as it continued to grow, because the lava wasn't very viscous, it wasn't super rich in volatiles, once the island grew above the water, it actually transitioned into a Strombolian eruption because we no longer had this external water to drive the explosivity. The other one, which I think I've been pronouncing wrong for years, but it's supposed to be Hawaiian or something, I don't know. Yeah, thank you.
We learned as well actually when Australia we were with our promotion.
Oh, you did? Okay.
We were there and they kept being like said on cups and everything, it's pronounced like this.
I used to say Ayafliatlayokel, and then I looked up a YouTube video on how to pronounce it, and I was like, that's not right. So yeah, this was obviously a very famous one because it disrupted flights in Europe, and everyone was pissed off. But this erupted under one of the ice sheets on Iceland, and so the water came from melting ice, and that created a phreatomagmatic eruption. Now that one is actually an andesite, so it may have been more inclined to be explosive anyway, but I believe it's classed as a phreatomagmatic. Yeah. So yeah, the tight locality in Surtsey is a basalt, but it can happen in other compositions. So Ayafliatlayokel or something, and this other one that I'm going to talk about called Hunga Tonga. They're both andesites. Hunga Tonga is really cool because it went off this year. So this island emerged in 2009, and there was another big phreatomagmatic eruption in 2014 to 2015. But this is the 2015 eruption. you can see it's fairly explosive, and we have a big volcanic plume here and some kind of ash and gas column here. And what was left behind was a new island. And this is called a tuff cone. A tuff is basically just made up of ash from an eruption. And we'll talk a bit more about tuff next week. But then earlier this year, it had a giant phreatomagmatic eruption. And I believe this is one of the more explosive phreatomagmatic eruptions that's happened. And it resulted in a huge eruption column, 30 kilometers high. So I've got a video of it erupting that maybe we can watch. Okay, if it ever works. So this is just a picture, but that'll come into the video. Is that playing? Yeah. Sorry. Just for a bit of context, these guys were 15 kilometers away from the eruption. So. All right. Okay. So that was a giant phreatomagmatic eruption. And coming back to this VEI, Volcanic Explosivity Index, this one was between 5 and 6, so it was really, really huge. I think more typical for these phreatomagmatic ones would be somewhere in the region of 4 or 5. Yeah. There's also something called Phreatic eruptions, and I don't want you to worry too much about the difference between these, but I have included them because you'll probably find them if you ever look this stuff up, or if you're ever reading about Phreatomagmatic. They're basically the same, but they're defined by there's no molten lava involved. So they're sometimes called steam blast eruptions. So the idea is that they're only blasting out fragments of pre-existing solid rock from the volcanic conduit rather than blasting out chunks of fresh lava. The problem here is they're quite hard to distinguish because if you imagine a lot of the rock that's in the volcanic conduit is just previous lava. So where do you draw the line between like a fresh lava that's frozen or an older lava that's come out of the conduit? It's not particularly straightforward to tell them apart. So yeah, same idea. We're flash heating steam, we're fragmenting rock, and we're propelling an eruption. So this diagram here is actually for Phreatomagmatic, but in this case, the magma is interacting with groundwater and exploding, and that's causing our eruption column and these surges off the base of it. Okay, so basalt eruptions range from high flow rate fire fountains or curtains. These are Hawaiian eruptions, and that's for eruptions of low viscosity, low volatile content lava, such as tholiites. On the other end, we get these kind of mildly explosive Strombolian eruptions, and these are for more viscous or high volatile content lavas, such as basaltic andesites or alkaline lavas. Basaltic eruptions are only explosive when we've got a bit of help from external water, and that water can fragment the magma, flash heat to steam, and it drives a phreatomagmatic eruption. And we can use the Volcanic Explosivity Index to measure eruption intensity. Most of these basaltic ones are very low VEI, except for the extreme end of the phreatomagmatic ones. Does anyone have any questions about that section? Oh. All right, explosive silicic eruptions. So the vast majority of explosive eruptions happen for more viscous silicic magma compositions, and volatiles are always important here. So yeah, back to our kind of reference diagram. We're in this end, high viscosity and high magma rise rates, and they're always going to be explosive. So there's three main types. There's Vulcanian, which typically happen in basaltic andesite to dacite magmas, so fairly evolved, but not the high end of things. There's Peléan, which are andesite to rhyolite, and there's plinian, which are usually dacite or rhyolite. You can see as well that here the volcanic explosivity index is going upwards as we go through this towards more evolved, more viscous compositions. And just a reminder again of the log scale here. I think this is quite a cool image because it shows it. The area of the circles is proportional to how much stuff is erupted. Go ahead.
Just to the prior slide.
Yeah.
All of these kinds of eruptions, are they only on land or do they count as well as descriptive of something that's submarine?
I think so. I'm just trying to think. Yeah, I think all of these would have to be on land. I'm not actually sure what would happen. So with the plinian one, it's probably the most obvious, and you'll see why when we get to it. It's because volatile expansion and depressurization is so important. Yeah, I'm not sure how these things would grow if they erupted underwater. If it's shallow water, you could get these Phreatomagmatic eruptions, but yeah, I don't know. We'd have to look at somewhere where like you had an island arc just starting up, right? Yeah, good question. Okay, so yeah, on our volcanic explosivity index, you can see that when we talk about 2 to 3, that's these thousandth or 100th of a kilometer cubed, and at the extreme end, an 8, we've got 1,000 kilometer cubed. So this is just vast differences in how much is being erupted. Okay, Vulcanian eruptions are essentially the same process as Strombolian, but with a more viscous magma. And so we have the same idea that gas is rising up through the conduit, so the gas is still able to move independent of the magma and flow upwards. But when it gets to the top, there's this cool cap or plug, which is basically solid and behaves in a brittle manner. And when that gas pressure builds up enough, the cap fails, it breaks, and it ruptures, and we have an explosive release of gas and rock from the magma conduit. These are fairly intermittent explosions, so you can get repeated Vulcanian eruptions over time. And they are not as dangerous as some of the other ones that we're going to look at, although I believe they're not exactly safe either. Typically at moderate plume heights, they can go as high as 20 kilometers into the atmosphere, but most of the time this plume of this eruption column is only going to be less than 5 kilometers tall. Peléan eruptions are kind of their own thing, and I'm not quite sure that I understand the mechanisms between them, but basically they're caused by catastrophic collapse of a lava dome. And what I mean by that is it's not just some stuff from the top and sides rolling down. The lava dome collapses and it triggers an explosive eruption. They're kind of defined by the fact that this dome collapse forms something called a pyroclastic flow. And now's a good time to talk about pyroclastic flows because we need to understand them for the plinian eruptions as well. A pyroclastic flow is basically a density current of hot ash, gases, crystals, and lithic fragments, which are chunks of rock. So we've already talked about density currents in the context of flows of crystals and magma down the side walls of magma chambers, right? And this is a similar thing. Basically comes about because this mixture of ash, gas, crystals, and lithic fragments is denser than the air around it, so it flows downhill. They move really fast, so up to 200 meters per second, something like 700 kilometers an hour. So if you ever watch a volcano film and they're driving away from pyroclastic flow in a car, that doesn't happen, you just die. So you don't want to be in the way of one of these. And because they've got all these, this ash, which is just frozen lava, and all these volcanic gases, they can be incredibly hot, up to 700 degrees C. So imagine something moving downhill, 700 degrees C, 200 meters per second, it can wipe out everything in its path. They're incredibly destructive, and they're probably the most dangerous hazard from volcanic eruptions. So here's a figure showing a few of the different ways that pyroclastic flows can form. The one, so the Peléan one that I've been talking about here, this dome collapse, This style of eruption was named after Mount Peléan. And yeah, the dome collapsed and it blew a pyroclastic flow out the side of it. We also get them in Plinian eruptions. So the typical one is that an eruption column eventually collapses, and we'll talk about that in a bit. Or in special cases, so Mount St. Helens was quite a bizarre eruption where there was actually a sideways blast, and that formed a pyroclastic flow coming straight out the side. All right, and the final one, and it's the one that I'm going into most detail on, because it's probably, to me it's the most interesting, the biggest eruptions, they're cool. Yeah, this is a Plinian eruption, and it's named after Pliny the Elder, who's maybe, I don't know, maybe call him the first volcanologist. And it was described for the 79 AD eruption of Vesuvius that buried Pompeii and Herculaneum. So it's actually quite a good description that I've got the quote of here. A cloud from which mountain was uncertain at this distance, but it was found afterwards to come from Mount Vesuvius, was ascending, the appearance of which I cannot give you a more exact description of than by likening it to that of a pine tree, for it shot up to great height in the form of a very tall trunk which spread itself out at the top into sort of branches. It appeared sometimes bright, sometimes dark and spotted, as it was either more or less impregnated with earth and cinders. So he's actually got a lot of the key features of a Plinian eruption, is that we have a tall eruption column that branches out into a lateral cloud, and it's not just gas, it's full of earth and cinders, chunks of lava. So not bad Pliny for the first century. So Plinian eruptions are the most explosive eruption style, and these are driven basically just by volatile exsolution. So what's happening is that the magma in the conduit is very viscous, and so as volatiles are exsolving, they can't escape. So these volatile bubbles, they form and they grow, and as they're exsolving, the combination of the magma plus the bubbles is less dense than the rock around it, so the magma begins to ascend. At that point, we actually exsolve even more volatiles because we're reducing the pressure, and we make the magma less dense again. Because we're exsolving a bunch of water, the magma is becoming increasingly dry and becoming more and more viscous. So it's more likely to break and fragment. If the rate at which it's being deformed is too high, it will act as a brittle glass rather than as a ductile fluid. So basically have this positive feedback between magma rising, more exsolution, becomes less dense, rises even faster. And it reaches this threshold, which is either from a bubble concentration reaching some sort of critical amount, which is usually quoted as 75%, or the melt becoming too brittle because of the strain rate and the increasing viscosity. But in any case, the magma basically gets ripped to shreds, and it's propelled out of the vent at incredibly high speeds. So if we look at some chunks of ash from a Plinian eruption, you can sort of see little fragments of what's happening. So these are obviously quite small, but you can see these rounded things are the remnants of bubbles, but they were just completely torn apart. You can see here this might have been a bigger bubble or something, but it ends up just being like a filament of glass. This is almost like a foam after it's popped, but then it's just been frozen in place. So yeah, this diagram kind of sums it up. We start in a magma chamber and begin exsolving stuff. We have magma and an increasing amount of bubbles. When we hit this fragmentation level, it's no longer really like a coherent magma with bubbles in it. It's just this mess of gas and pyroclasts, which are these shredded up chunks of magma. And so as we go upwards to lower pressures, the volume fraction of gas compared to magma is going up and up and up, and eventually it becomes mainly gas. The pressure is dropping, and the velocity goes up basically exponentially towards the end. All right. So we need something to kind of kickstart this process of exsolving volatiles and then start this positive feedback where the magma is ascending at ever faster rates. So there's a few ways you can do this. It could just be crystallization. We increase volatile contents until we hit saturation because the volatiles are incompatible. It could be recharged with a fresh batch of hot magma that heats everything up and forces volatile exsolution. Or it can be sudden decompression, and probably a pretty good example of this in Mount St. Helens, where what happened is an earthquake triggered a landslide, and basically the side of the mountain just slid off. And so all this weight that's on top of the magma has just been removed. So we've depressurized it. And so that instantly caused volatile exsolution through decompression, and then we start this process. And it began with a lateral blast, and it became a plinian eruption. Because they're so explosive, they're coming out of the vent up to 600 meters per second. There's this huge thrust coming from the gas expansion, and they can make these huge volcanic plumes up to 45 kilometers high. In the initial part, it's being driven by this thrust out of the vent, but this mixture of ash and hot volcanic gases actually mixes with the air around it. They call this air entrainment, so air is being pulled into the plume of volcanic gas and material and being mixed in. And then this plume of volcanic gas, heated air, and ash ends up being less dense than the atmosphere around it. So it then becomes buoyant and basically floats upwards. As it goes, it's beginning to cool, it's interacting more with the air around it, and eventually it hits this layer of neutral buoyancy where it can't rise anymore, and then it spreads laterally at that layer, and it might get dispersed out by the wind. So at some point the eruption can't sustain itself, and that might be because we've run out of lava to erupt, or the magma chamber pressure has dropped too much. And at this point the eruption column can't keep rising, and it basically collapses back on itself. And this is what we were talking about before in the pyroclastic flow slide, is then this just collapses downwards and it makes a density current. This is now cooled or entrained enough air where it's no longer less dense than the air around it, and we get a downwards flowing density current, and that triggers our pyroclastic flows. The final one to mention are something called ultra-plinian eruptions, and these are just really, really big plinian eruptions. So the only distinction is how big they are. So Yellowstone is pretty famous as being a super volcano. It's the largest volcano on Earth. It's about 65 kilometers across in diameter, absolutely massive. And this is sat on a huge rhyolite magma chamber, which is still there, and it's still molten, and there's still a bunch of activity related to it, like we get the geysers, and there's all sorts of fumaroles and volcanic gas emissions. And the Yellowstone volcano has got this time progression. People often describe it as being a sort of plume underneath the continent, so the continent's moving over the surface of it. And it seems like about every 600,000 years we get a huge eruption. So there's the Henry Fawkes caldera at 1.8 million years ago, there's the Big Ben caldera at 1.2, and Yellowstone last erupted 600,000 years ago with one of these ultra-plinian eruptions. So yeah, a lot of disaster films focus on this one. So yeah. Okay, so just to put it all together, this is kind of a summary of eruption styles, and here it's plotting kind of explosiveness. So this is the tephra, the stuff ejected, getting finer and finer as it gets fragmented more and ripped apart. And on this axis is the height of the volcanic plume. So basically, the more explosive, we're getting more fragmented tephra and greater plume heights. And generally, we're going from basaltic here through, kind of maybe basalt, basaltic andesite, and then to increasingly silicic eruptions. The only difference is this, the Phreatomagmatic ones here, which in this diagram they call them hydromagmatic, but it's the same thing. These you can get very explosive eruptions, even if it's a basalt. So that's kind of the outlier. All right, so silicic explosive eruptions increase in intensity from Vulcanian to Peléan to Plinian. Vulcanian eruptions are more viscous or silicic equivalent of Strombolian eruptions. Peléan eruptions are driven by the collapse of lava domes, and they have to have pyroclastic flows, otherwise it's not a Peléan eruption. And plinian eruptions are driven by this positive feedback of volatile egg solution, reduced magma density, and increasing viscosity, and this causes explosive fragmentation and the formation of these huge volcanic plumes. These will eventually collapse and make pyroclastic flows. Does anyone have any questions about that? All right. Oh yeah, good.
Is that always basaltic?
No, I think so. It can also happen in other compositions, but it's just I brought it in the basaltic one because that is the only way that you get really explosive basaltic eruptions. Okay, whoops. Reading this week is Gil chapter 7. Have a chill week because it's first one back from New Year's. So. And there's the lecture summary. So you're all free to go.